Number 39. The experimental apparatus represented above is used to demonstrate the rates at which gases diffuse. Okay. When the cotton balls are placed on the ends of a tube at the same time, the gases diffuse from each other and meet somewhere in between where they react to form a white solid. So, apparently, some gases escape out of that cotton ball over here as well, and somewhere in the middle, they're going to react and form a solid. Okay, which of the following combinations will produce a solid closest to the center of the tube? Now, if you guys think about it, let's just think about how they would even meet halfway to begin with, right? Just like hypothetically, think about it this way. Imagine the gas coming out of the aqueous HX is like a lot faster, right? Then what's going to happen is it's probably going to go all the way over there. And then in the meanwhile, this, I don't know, the gas coming out of the volatile base, maybe this is like really slow. So in that meantime, it was only able to go that much. So more likely that they're going to meet around this point way more than halfway for the HX, coming out of the HX, than the one that's coming out of the volatile base. I don't know if this makes sense, right? So, the point is, if they were to meet exactly right around that halfway, well, in that given period of time, let's say, I don't know, we let it react for like 15 minutes or whatever, right? If they were to react right around in the middle and then form solid or do whatever, honestly, right? What we need to guess is that probably how fast they came toward each other was probably similar, right? AKA the rate of diffusion for the gases must have been very, very close. Now, how do you find the rate of diffusion, right? It's that little equation, URMS is equal to square root of 3RT over the molar mass, right? Well, y'all don't really need to actually do any calculations here. The point is this: if they have similar, very similar diffusion rates, then that probably means they have very similar molar mass, right? Because think about this equation. 3 is a constant, R is a constant, temperature is temperature, and whatever the temperature it may be inside that tube, it's going to be the same for both gases anyway. So everything else is the same except the molar mass. So if they have very, very similar diffusion rates, they better have very, very similar molar mass. So that was the point of this question. So, well, let's look at some of the elements we have here. Chlorine was 35.45. I'm just going to say 35 for the sake of easy math. Hydrogen, I'm just going to call it 1. Nitrogen is 14. Carbon is 12. And we have bromine, which is 79.9, but I'm just going to say 80. Okay, so let's kind of take a look. Starting with A. Well, so that's going to be 36. And this one's going to be 3 and 2 and 14 and 12. So that would be a total of 26, 28, 31. So 36, 31, not the very closest, but it's not too far. So I don't know, maybe. And then choice B, 36, and that's going to be 17. Way far out. C, that's going to be 81, and that's going to be, 36. I just had that from above, or 31. Sorry about the 31. But the point is, super, super far. Very different. And then 81 and 17, very different. It's probably A. Once again, to explain the whole idea, these two gases have very, very similar molar masses, aka in terms of how fast they move around, we call it diffusion rates. It's going to be pretty similar because they have very similar molar mass.